we're just going to look at stats. This is a kind of tidying up loose ends, finishing up. Since there was a set of things that hadn't put in the lessons that we've done so far, so I kind of thought, okay, maybe put this at the end of the lesson that we were doing before. But then I went, that's just getting that bit longer, and I want, it's easy to put everything into a 10-hour lesson, but that's kind of not that useful. I mean, to demand that the viewer spends that huge amount of time to get through the material, which can be done faster. So it's always a balancing act between, you always want to not zoom through the material. I mean, it's also easy to just go, oh, we can fit everything in and we'll do it in 20 minutes. But you basically have 10 weeks over the 2 years to cover this material. So doing it in 2, maybe now 3 weeks is still very quick. So again, this is a kind of tidying up loose ends kind of lesson. So it's also a lot. It shouldn't be that long. So we'll see how it goes. The first thing we want to look at is the idea of, I suppose, sampling variability. So let's think of an example. If you just pick 5 cards. Now you could pick all 5 the same suite. They could all be clubs. And in particular, if you just open a new pack of cards, they're typically put in order. So you'd have all the diamonds together, then the clubs, the hearts, and the spades. So if you just pick the first 5 cards, they'd most likely be from the same suite. So pick 5 cards, and they could be from the same suite. So say, imagine that they're could get let's say 5 clubs. Now, that's the kind of issue that we want to think about and look at in this lesson. That probabilistically, actually the chances of that happening are very low if the cards were randomized, if they were shuffled, say. Because the probability of picking 1 clubs is, say, 1 in 4. The probability of getting 2 clubs in a row is 1 in 16. Again, if it's randomized, and if there's no if there's the same chance of any of the suites getting picked. So to pick 5 clubs is a quarter times a quarter times a quarter times a quarter times a quarter. So 1/16th, 1/64th, 1/256th. So basically 1 in 1,000. Though of course it can happen. Like, you can win the lotto. It's just very unlikely. So knowing that there's this random element, if I pick a sample, because I'm using a sample since that's more convenient, but I want to actually know about the entire population. So I use sample since convenient. It's it's cheaper. It's practical. It's far more practical. But there is this random element that if I did pick 5 cards, I could, with a 1 in 1,000 chance, end up with 5 clubs. So then, if I was commenting on that pack of cards, and the only information I had was, my sample of 5 cards, which were all clubs, then, I'd be forced to think that the entire selection of the entire pack of cards were all clubs, because that's what the data says. So yeah, what can we do? I mean, so knowing this, does that mean that using samples are meaningless? I mean, should we not use samples at all? Well, we more want to take a few things from this observation, learn some lessons in a way. So first of all, well, be aware of this variability. So, when you pick 5 clubs, now if you're aware that there is variability, that you're warned that, okay, yes, I might have gotten 5 clubs, but, samples don't necessarily have to be representative. You could just randomly end up with a strange selection. So if you're aware of rule number 1, be aware of variability, or of this variability, then you won't be fooled. You won't be overconfident about what you know. All you have is that you got 5 cards that were clubs, but there is variability. So the second thing would be, well, how can I safeguard against this variability? How can I reduce its impact? So, and we'll be looking at this more later. The basic trick is, well, use more cards. So increase n. So where n is, in this case, the number of cards. So I mean, already with 5 cards, the likelihood that you'll end up with 5 cards which are all clubs is, something like 1 in 1,000. So if you picked yet another card, well, then it would be something like 1 in 4,000. And in fact, if you've gone through the probability and stuff, you could be putting your hand up in the back and going, but this is a case of without replacement. So when you pick the first card, the chances of picking of clubs are 1 in 4. But if once you've picked 4 cards, well, then there's not many, there are only, say, 7 clubs left, while there are 13 of the other suites. So the probability of picking yet another club is actually now no longer 1 in 4, it's closer to 1 in 8. So the chances of picking 5 clubs is, even smaller than the 1 in 1,000. But by increasing n, so picking 6 cards, the likelihood is even smaller. And that's what we'll look at that and see what impact picking more has to basically increase our confidence in in our sample, and in making statements based on our sample. And finally, it just reminds us of random. So, if you just got a pack of cards which are brand new, and the cards are in order, so you would have the 13 diamonds in a row. So, and if you just pick the first 5 cards, they could all the probability that they are all diamonds is actually far greater, or the probability that they're all from the same suite is far greater. While if you randomize, if you were to either shuffle the pack or just randomly pick your cards from the pack, then you should get a more representative, unbiased representation of the entire population, of the entire collection of cards. So if you picked 5 random cards, you're more likely to end up with having 2 or 3, if not 4 different suites, and that will give you a far better impression or representation of the entire pack. So when you would make comments based on the randomly chosen 5 cards, that would be pretty representative of the entire population or the entire pack of cards. So that's the first thing we wanted to say. Next, just wanted to remember the histogram. I think we briefly touched on this, and we're not going to be saying much here either, but just a quick reminder. So with a histogram, so this would be an example of a histogram. You have boxes or rectangles. So if there were, you'd have a range. So this is, say, 1, 2, 3, 4, 5. If you were picking, from 5 different things. So for every 3 that you got, the height here would increase. For every 2, the height of the 2 box would increase, and so on. And otherwise you could have a range. So instead of 1, you might have up to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1 to 9 is, for every time you got a number which was 1 to 9, you would increase the height of this box. Every time you had a number from 10 to 19, you increase this one, or whatever. Whatever range you were using. So what I just wanted to comment on was, once so I suppose there are 2 things I wanted to immediately to start off with is, well, if you draw your histogram for your whole population, so say you took all the students in a year, and you did some survey, and then you drew a histogram, and say you got a shape like this. This is, say, the entire population. So this is for entire population. Now, if you then instead took a sample, which was random, then you would expect to get exactly the same shape, because a random sample, it shouldn't have any reason to have a bias. So, okay, the specific numbers would change because your sample might only have 15 people as opposed to 150. So of course, if you add the number in each of the boxes, so 1, 2, 3, 4, and 5, that should add up to the entire number of people you're talking about. So for the entire population, it should add up to 150. If you're dealing with your sample, it should add up to 15. Now, what you can do with the histogram is you can kind of comment on the shape. And so this, which is also called the distribution. So which ones are, or which ones have different, or these are the different frequencies for each of the different ranges or numbers, depending on whatever you're looking at. So what you would then be interested in noting when you see a distribution is, well, is it symmetric? Well, in this case, it seems to be. You have a peak in the middle, and then 2 and 4 have the same height, 5 and 1 have the same height. In other cases, the distribution can be skewed. So it could be that you have a peak on the left-hand side and then a long tail on the right-hand side. Or it could be that you have a long tail, then the peak, and a short tail on the right-hand side. So these would be skewed. So that's one. Those are the kind of comments that you can make based on your histogram, and you can create your histogram based on your data. So these would be univariate data, and you just it could be for the entire population, or it could be from a sample. Then just wanted to comment on the empirical rule. So that is that for a normal distribution, this is exactly true, and the empirical rule is when you just apply that rule to a distribution in general, because the normal distribution occurs very frequently, so it's not a bad guess as a starting place. It is an empirical rule. It isn't exact. It's not necessarily true, but as a rule of thumb, as a starting place, it's reasonable. So if your average, say, I'm thinking about shoe sizes, because shoe sizes are normally distributed, and if your standard deviation is, say, 3, well, the empirical rule says that average plus or minus one standard deviation. So if, say, whatever this data is, 1, 2, 3, 4, 5, if the mean is 3 and the standard deviation is 1, so then the data, so the data which is 2, 3, or 4, like that central block, so the average plus or minus one standard deviation, that contains 68% of the entire population. And should be for the sample as well. I mean, unless it's not a representative sample. And on top of that, your average plus or minus 2 standard deviations. So that'll include a bigger basket of people or of your population. Well, that contains 95% of the population. So if this was the correct data for shoe sizes, it would be that if you had shoe sizes, if your shop stocked shoe sizes from 3 to 9, that's plus or minus one standard deviation. So then 68% of the people, if they all had a look in your shop, you would have the correct shoe size for them. So yeah, if shoe shop stocked sizes 3 to 9, that's 68%. If, on the other hand, you stocked sizes, well, yeah, I suppose 2 standard deviation would be 0. So I'll just call that 1. So if I had 1 to 12, that's that would be, you'd have shoes that would fit 95% of the population. And that's the kind of thing that you would get in a shoe shop. You know, that's why, you know, you have the special shoe shops for extra large feet, because the number of people who have shoe sizes 15, 16, 17 or higher is very low. So that's a far more specialist market. And if you knew that, you know, or since you know that shoe sizes are kind of normally distributed, that lets you stock correctly. You can say, okay, I should have 50 pairs of size 6 shoes, and then maybe 30 pairs of size 7 and 6, because they're not. And in fact, from your normal distribution, you know exactly how much lower the number of size 5s are and the number of size 7s are compared to the number of people with size 6. So you can just stock accordingly, and you'd know that the number of people shoes that you need for size 12 would be far slower or far lower. So the empirical rule is just a handy rule of thumb, so that you kind of know that, okay, I'll basically try and deal for people who are plus or minus 2 standard deviations from the mean, because that's the vast bulk of people. That will cater for 95% of people. And in a way, you can say the other population, they're kind of more outliers or extremes. So actually, that brings up to the last point. So that is to deal with hypothesis testing. So in particular, I'm just going to look at the example of polling. So, you know, whenever you have a poll, you know, when you have an election and stuff, you'll get, you know, a candidate A or, you know, party A has a popularity of, say, 40%, and then B has maybe 28%, and then there'd be C, D, and E, and many others, so, and which would roughly add up to 100%. Now, that you kind of know already. You've heard about that. So the thing we're just going to end on is the concept of margin of error. So in short, the rule, the thing you want to remember is 1 over the square root of n. That's how you work out the margin of error. So if you have a sample of 400 people, and you know, from that sample you got that 40% are going to vote for candidate A, 28% are going to vote for candidate B, and so on. Well, then using this rule, you know, the margin of error rule of 1 over the square root of n, that means it's going to be 1 over the square root of 400, which is equal to 1 over 20, which is equal to 5%. So if our margin of error is 5%, then when we report what our poll results are, we're not just going to say candidate A has a popularity of 40%. We'll add plus or minus 5%. Plus or minus 5%. This is a rough estimate. In reality, you would multiply this. The expression is a slight variation of this, but the main idea is that the error is proportional to 1 over the square root of n. So if you want greater accuracy, you want to increase the n, the number of people you poll, and the rate at which the error is going to decrease as you increase n is 1 over the square root of n. So that's all I wanted to add to the previous stuff that we've done already, which wraps up our look at statistics. So we'll move on to the number strand next.